Kids love fossils. Of all the exhibits in a museum that really gets a school group enthusiastic, it's the fossil hall. I guess I'm just a kid that never grew up, for I get the same feeling when I wander through a collection like this at the Smithsonian. I think the wonder comes in part from the imagination. As magnificent as lions, elephants and whales are, we know what they look like, know how they fit into the rest of the ecosystem, the reality we currently live in. For fossils, it's different though. Until the invention of a time machine that can travel to the past, which Professor Hawking informs us is not going to happen, there will always be that element of the uncertain. That is not to say we can't get very close to understanding how these creatures once lived and interacted, but there will always be room for the imagination to play. And that is where the wonder comes from. This fascination is wonderfully demonstrated in the National Museum of Natural History and the research that is conducted in the Department of Paleobiology. So in this episode, I'd like to ask, what is paleontology? Kind of fundamental question given the name of this series. So let's look at how paleontology developed as a science, what the chances are of becoming a fossil, what the common modes of fossilization are, and what is exceptional preservation. Fossils have been a part of human culture for a long time. You can imagine the legends that must have developed from dinosaur bones weathering out of a hillside, or a trackway of ancient footprints preserved in solid rock. I wonder how many stories of dragons and giants fossils like these have generated around a campfire at night. A very early reference to fossils comes from the 6th century BC and the Greek philosopher Xenophanes. Like most Greek philosophers, he wandered around the Mediterranean having an opinion on, well, pretty much everything really, from the nature of religion and the gods to a sort of critical rationalism. Xenophanes would also bemoan the rewards and reverence given to popular athletes, while philosophers like Xenophanes were underappreciated and ignored. Perhaps he just really wanted his picture on a piece of pottery. Apart from being somewhat miffed by the superstar athletes of the time, Xenophanes would also conclude from his examination of fossil fish and shells that water must have covered much of the Earth's surface at one time in the past. An important concept, showing that he understood that there was a deeper historical narrative to our planet that could be told by the use of fossils. Similar ideas were proposed by the Chinese naturalist Shen Ku in 1088, another wonderful overachiever, who, finding fossils in the Changjiang Mountains, decided that they indicated shorelines had shifted over time. He also found bamboo fossils in Shaanxi province, part of China that is currently far too dry for bamboo to grow, and concluded that climate change must have occurred at some time in the past. All this 900 years before Al Gore. Thoughts on how creatures could become fossils were proposed in 1027 by Persian polymath Avicenna, who speculated that fossils must have formed when a carcass was bathed in petrifying fluids. These are all really modern concepts. Concepts of sea level change and climate change, the passage of vast amounts of time and the processes that operate in the Earth to form fossils. And in the West, they would largely be ignored or forgotten. Things would change though, as our understanding and appreciation of fossils accelerates when we move into the 17th century, the age of reason. There are so many important figures who have contributed to the development of the science of paleontology in this period, it would be difficult to cover them all. But here's just a selection. This is Robert Hooke, an English natural philosopher who would make a significant contribution in his famous book Micrographia, published in 1665. The book was the first examination of the very small as revealed by Hooke's microscope. From his study of fossil wood, Hooke would conclude that these and other fossils were once living organisms that had been transformed into rock by the petrifying action of mineral-rich water. Incidentally, the image we have here of Hooke is somewhat conjectural, as no contemporary portrait of him exists. Hooke was a somewhat, shall we say, prickly character who managed to get onto the wrong side of, well, pretty much everybody, but also Isaac Newton, who, it is rumoured, when he became president of the Royal Society, made sure no images of Hooke remained. Sometimes the kids just don't play nicely in the scientific playground. Another extremely important figure is Georges Cuvier, a French naturalist and philosopher. Cuvier would make several significant contributions, including providing us with the concept of extinction back in 1796. When comparing the jaws of living elephants with fossil jaws of something similar, but at the same time distinct, we know it as the mammoth, Cuvier concluded that some species that used to exist on Earth were no longer around. A somewhat troubling concept to some, who thought that this idea challenged the notion of God's perfect and complete creation, a bit like a smile missing a number of important teeth. Indeed, this concept of extinction preyed heavily upon the mind of the third President of the United States, Thomas Jefferson. Jefferson was an avid naturalist and intrigued by the bones of ancient giants like the Columbian mammoth. Jefferson himself proposed the name Megalonyx, meaning giant claw, in 1797 for the bones of a giant ground sloth from the western Virginia, although at the time he believed them to be the remains of some sort of large lion. Jefferson firmly believed in the completeness of nature and expected that these giants would be found alive and well west of the Mississippi River. He even asked the explorers Lewis and Clark to keep a watch out for Megalonyx and other fantastic fossil creatures on their expedition of 1804 to 1806. It would be one of Cuvier's students, though, Henri-Marie Ducote de Banville, I love saying that, who would finally give the study of fossils a name. At first he chose the term Paleozoology in 1817, but by 1822, after a number of iterations, settled on the more inclusive Paleontology, which would cover both fossil plants and animals. As such, thanks to Henri, I and Dr. Ross Geller from Friends are both paleontologists. The son of a blacksmith, William Smith, would demonstrate the usefulness of fossils as a tool for correlating strata. By 1815, he published a groundbreaking geological map of England, Wales and southern Scotland, earning him the name Strata Smith. Importantly, Smith demonstrated that fossils provided the context for the development of a geological timescale. Once constructed, this scale would allow scientists to correlate across regions, ensuring they are on the same page of Earth's history, and in doing so, start to tell the story of Earth's deep evolution. This is an idea that would be taken up by Smith's brother-in-law, John Phillips, who in 1841 published the first geological timescale. He divided geological time into three eras that we use today: the Paleozoic, Mesozoic and Cenozoic. Although the names and the dates on the timescale would change considerably over time, paleontologists and geologists now had a yardstick which they could use to delve into the past. Another important development was the discovery of fossils in a quarry in the Neander Valley of Germany. They were described by schoolmaster Johann Karl Furholt and anatomist Hermann Schaffhausen in 1856. They were identified as belonging to a group of humans that were quite different to any modern people. They would eventually be named Homo neanderthalensis. And so, with these fossils, paleontology became part of our story too. And this is just 5 years after anatomist and founder of the Natural History Museum in London, Richard Owen, gave us the word dinosaur, probably the first scientific term any child has known ever since. And of course, who could forget this man? Charles Darwin, who, with the publication of The Origin of Species by Means of Natural Selection in 1859, would eventually provide the first hints of the mechanism behind the changing suites of fossils paleontologists have been finding. From here, the field of paleontology would explode into numerous disciplines and sub-disciplines, becoming an extremely important part of academic studies in universities and museums all over the world. North America has had its share of famous paleontologists too. For example, Othniel Marsh and Edward Cope, who would expand our understanding of the dinosaurs during the Great Dinosaur Rush in Colorado, Nebraska and Wyoming in the late 1800s. Marsh and Cope, of course, are also the paleontological poster boys for grudge-bearing in paleontology, as they try to financially and socially ruin each other's attempts to wreck the scientific career of the other. And coming closer to home, we should also include one of the most famous secretaries of the Smithsonian Institution, Charles Doolittle Walcott. In 1909, he would stumble across the Burgess Shale in British Columbia in the Canadian Rockies. But more of Charles Walcott later. What about the actual fossils? Without which, of course, there would be no science of paleontology. How can you turn a soft, organic, squishy organism into a fossil that can survive earthquakes, rising mountains, closing oceans, and colliding continents for millions, perhaps even billions of years? Just what are the chances of some organism becoming a fossil? To be honest, the chances of anything becoming a fossil are pretty slim. The fact that we have fossils at all speaks to the sheer numbers of individuals and species that have existed through time. With their countless billions, it would only take a tiny fraction of them, though, to fossilise, to leave us with a substantial record in the rocks. But let's consider those that actually do make it. What factors do they have in their favour? How do you maximise your chance of becoming a fossil? As my real estate agent would say, location, location, location. Just as being in the right place might maximise your chances of making a killing on the housing market, so being in the right place increases your chance of becoming a fossil. An example of a worse place to be could be something like a high mountainous region or an eroding plain. Now, this might appear odd when we consider an environment like the African savanna, so full of life. Shouldn't that be a great place for a fossil to form? Problem is, once, as John Cleese would have it, you kick the bucket, shuffle off this mortal coil, or go to join the choir in Visibule, your body just tends to lie out there in the open. In the case of the African savanna, you probably wouldn't lie out there for very long. Scavengers like hyena, vultures, would very quickly dismember the carcass with whatever remained, which is probably not very much by then, rotting to nothing under the influence of numerous microbes and our oxygen-rich atmosphere. To form a fossil, you need to get your body buried as quickly as possible, out of the way of the scavengers, and preferably sealed from oxygen or in at least reduced oxygen conditions. Now, this just isn't going to happen in an open plain. But if the subject in question happened to live close to a body of water, a river, or a lake, you now have a chance to being in an environment where you might be able to bury your corpse with sediment. As being buried in sediments is probably your best bet for becoming a fossil, it follows that organisms that live in aquatic environments, like lakes and rivers, will have a greater chance of becoming a fossil. It also follows that, on the whole, aquatic creatures that live in the oceans and other water bodies that are receiving vast quantities of sediment via rivers and streams will have a greater preservation potential than terrestrial land-based organisms. So where you live is important. But there's another important factor to consider as well, and that is what you are made of. Soft-bodied, squishy organisms like this octopus will have a much reduced preservation potential compared to, for example, one of its close relatives, the nautilus. Of course, the body parts of the nautilus will decay just like the octopus, but a significant portion of the original creature, its shell, will have a greater chance of preservation. This is why the fossil record of octopi is considerably poorer than that of their shelled relatives. Any creature that has a significant development of hard parts, therefore, will have a greater chance of preservation and a greater representation in the fossil record. This is a persistent bias paleontologists have to be aware of when reconstructing ancient ecosystems from fossil sites, especially when, in some settings, soft-bodied creatures lacking any skeletal components may have made up a large part of the animal assemblage. But considering hard parts for a while, life has used a variety of materials for production of structural support. Calcium carbonate or calcite is a very common mineral used by many organisms, including bryozoans, corals, brachiopods, mollusks, and many arthropods and echinoderms like sea urchins. Examples of silica-secreting organisms include sponges and the radiolarians, tiny marine protists about 0.1 to 0.2 millimeters in size that secrete these exquisite ornament-like structures out of biological glass. Calcium phosphate, usually in the form of the mineral apatite, is used for the skeletal elements, that's bones and teeth, of vertebrates and the feeding apparatus of the extinct chordates called conodonts. Now, the various skeletal components of these creatures will behave differently under different environmental rock-forming, what we call diagenetic conditions. Even slightly different forms of the same mineral can react very differently to the processes of fossilization. Consider these two fossils, an ammonite cephalopod, relative to the Nautilus, and a brachiopod, a creature that might look like a clam, but is actually more related to the bryozoan moss animals. Both creatures use calcium carbonate in their shells, but not all calcium carbonate is the same. The ammonite is composed of a mineralic form called aragonite, while some brachiopods use the more typical calcite. The main difference in the two forms of calcium carbonate is in the arrangement of the atoms that make up the crystal lattice. This might sound like an esoteric difference, given that chemically they're very similar. But when the two substances are buried, they behave quite differently. Aragonite is only really stable at surface temperatures and pressures, while calcite is stable over a much broader range. The practical result is that organisms composed of aragonitic shells are more likely to be altered to calcite during fossilization, a transformation that might not result in the destruction of the fossil, but very often removes any of the fine internal details of the shell. If an organism is already composed of calcite, like the brachiopod in our example here, then there is likely a greater chance of detail being preserved, like you can see in the laminations in this fossilized shell of a carboniferous brachiopod. The laminations here represent the individual layers that the brachiopod secreted over its lifetime, like rings on a tree. Another consideration is the proportion of organic material present in the mineralized material. For example, trilobites, like these from the Lower Devonian of Oklahoma, would have formed extremely robust cuticles impregnated by the organic molecule chitin, but with a very high proportion of calcium carbonate. Fellow arthropods, the Malacostraca, that include shrimps, crabs and lobsters, have a much higher proportion of organic material in their exoskeletons, and as a result, they have a reduced preservation potential and a poorer fossil record. Insects also have a modest preservation potential, but because of their sheer abundance, they have a better fossil record than would be predicted from their exoskeletal durability alone. But it's not just the durability of the materials, calcium carbonate, silica, calcium phosphate, cellulose and chitin, that we have to consider. Another factor is how the material is organized. For example, arthropods consist of numerous exoskeletal body parts called sclerites. These tend to separate after death, giving us vast quantities of components of specimens in the fossil record. The same is true for sponges, which are composed of discrete structural elements called spicules, some as large as 2 millimeters, but many less than 60 microns in size. As a result, the various scaffolding units of sponges, like you can see here, are also common in the fossil record, more common than fossils of the original complete organism. It's a bit like an archaeologist finding the bricks and rocks that make up a large building rather than the building itself. Corals, however, like these from the Ordovician period of southern Ohio, secrete a single robust skeletal element, and as a result, the preservation potential of the entire organism is better than that of the sponges. So you see how a whole number of factors come into play when considering the preservation potential of a fossil. Location and mode of life of the original organism, the presence or absence of hard parts, the composition of those hard parts, and whether the organism contributes several cast malts during its lifetime. And of course, there is pure blind luck. So fossils like these beautiful silicified marine organisms from a Permian reef in Texas, although quite abundant, are still a marvel when you consider the vast numbers of individuals that never made it into the fossil record. We have to remember, though, that each of these preservational factors we have described creates a bias, with certain environments and/or organisms having a greater representation in the fossil record. An understanding of preservational mechanisms can also help us with miscomprehensions about the fossil record. For example, a common question I've been asked about the meteor impact that killed off the dinosaurs and a whole bunch of other creatures at the end of the Cretaceous 66 million years ago is, if a meteor wiped out the dinosaurs, why don't we find their fossils all packed around the horizon that marks the impact event? That is a good question, and is answered nicely by something called the Signor-Lipps effect. This was proposed by Philip Signor of the University of California, Davis, and Jerry Lipps of the University of California Museum of Paleontology, and is all about the factors we have been discussing. Basically, the Signor-Lipps effect states that it is very unlikely that the very first or the very last member of a particular fossil species in time will be found. This is due to the points that we are able to sample at any given time in the geological record. Consider the African savanna again. This is how we imagine it, isn't it? To quote Mr. Cleese once more, herds of wildebeest sweeping majestically across the plain. But let's be honest, even on a safari vacation, you still have to go looking for these creatures to photograph them. Most of the time, the African savanna looks like this, with apparently not much happening at all. Now add to that the fact there is only a minute proportion of those animals that live in that environment actually become fossils, and you can see why we may have a lack of fossils at any one geological horizon. There is more though. When you are looking at a geological horizon in time, you are mostly looking at a discontinuous two-dimensional slice through what was once a vast three-dimensional surface upon which creatures may or may not have been fossilized. As such, the chance of actually locating a dinosaur fossil at a very specific horizon in time, even after such a catastrophic event, is very small indeed. So you can see, it is probably only a very small proportion of any iteration of the biosphere that is going to get preserved, and there will likely be biases that may control the number and types of fossils that we do find. I don't want to sound too disheartening here though. The fossil record is still very powerful and an enlightening tool, but should be treated carefully. Given that, let's look at some of the ways in which creatures become fossils. A common mode of fossilization is the production of moulds and casts. Moulds are negative impressions of an organism that preserve information about the surface of a creature. A mould will commonly be produced when circulating pore waters moving through a sediment dissolve away the original skeletal material. Paleontologists will occasionally inject epoxy resin into the mould and then dissolve the surrounding rock to free the cast. Casts can form in the same way in nature when the mineral-rich waters deposit various minerals into fossil moulds. Fossils can also form by a process called carbonization. Here, a process of distillation caused by the heat and pressure of burial preferentially removes the hydrogen and oxygen of the soft tissue, leaving the carbon behind. This is a common mode of preservation of many land plant fossils, but also of these beautifully preserved graptolites that used to float through the Silurian oceans over 423 million years ago. Some of the most spectacular preservation, though, occurs when mineralizing fluids percolate through sedimentary units. Minerals are precipitated in spaces within skeletal materials of shells and other original structural materials, hardening and stabilizing the fossil. This mode of preservation is called permineralization and can preserve wonderful detail. For example, this image was taken on a scanning electron microscope and shows the cancellous, that spongy tissue, from the femur of a dinosaur magnified many times. You can even make out the honeycomb structure that added support and strength to the bone, faithfully preserved. The same processes can occur in some circumstances when organic material becomes completely replaced by the mineralizing fluids, a process called petrifaction. This can occur in both plant and animal fossils, but possibly one of the most spectacular examples comes from the petrified conifer forests of Arizona. An example of one of these trees stands outside the museum today. The fossils come from the late Triassic period, about 225 million years ago, when Arizona was humid and subtropical. The trees were living on the edges of streams and rivers, some growing up to 200 feet tall. Occasionally, they would fall into the water and get buried in sediments that contained high proportions of volcanic ash that was rich in silica. It's this volcanic ash that is the key to their preservation. Fluids carrying this dissolved mineral percolated through the sedimentary pile, seeping into the waterlogged trees and replacing their organic material with silica. The wonderful colours you see in many of these fossils are due to secondary minerals such as iron oxides like hematite that gives us the reds and purples, and limonite which gives us the yellow. So numerous are these fossil trees that in the past they've been used as building materials. Although internal detail is not always preserved in them, some of the logs and some of the animal bones found in these deposits show detail even down to the cellular level. There are, of course, other, rarer modes of fossilization that can produce spectacular material. Perhaps the most beautiful are those fossils trapped in amber. This is an important mode of fossilization for insects and spiders, but other life forms like small vertebrates and plants have been preserved as well. Amber forms when resin produced by a number of trees, but particularly coniferous trees, secrete resin to heal an injury or act as a defense. This oozes down the tree trunk, sticking and trapping creatures as it goes. Once the resin is buried, pressure and temperature will increase due to the overburdened pressure of the sediments, and this causes the organic chemicals in the resin to oxidize and polymerize, eventually hardening into amber and preserving the creatures it trapped in fantastic detail. Between 1981 and 1985, through the efforts of entomologist Don R. Davis, the Smithsonian acquired a wonderful collection from the Dominican Republic between 21 and 50 million years old. This collection is housed in the Department of Paleobiology and is a valuable resource today to fossil insect researchers throughout the world. It was collected by retired Army Major Jacob Brodzinski and his wife Marianela Lopez Peña. The Brodzinski-Lopez Peña collection comprises just over 5,000 specimens, providing a wonderful window into the early Miocene insects, mites, centipedes and spiders, but also leaves, flowers and even a bird feather. It is particularly useful for paleontologists as the amber is very pale, which allows a better view of the fossils. The preservation is just spectacular. In this sample, a small mite was clinging to the leg of this winged ant when it was trapped in the resin. And here, a new species of wasp. Just look at the level of detail down to the fine hairs on the insect's body. Another, as we might say in my hometown of Manchester, gobsmacking example of exceptional preservation housed at the Smithsonian comes from northwest Montana along the edge of the Glacier National Park. This particular rock in question comes from a unit from the Middle Eocene about 46 million years ago, a bit more than twice the age of that Dominican amber we just described. The deposit is called an oil shale due to the high amounts of organic material it contains, and it formed in the calm, shallow regions of a lake. The sediments are finely laminated and represent seasonal changes in deposition. Such laminations are called varves. During warmer periods, probably during spring and summer, when organic production was high, we see dark organic rich layers. These alternate with more wind-blown material, mineral material from cooler parts of the year. Dale Greenwalt, a volunteer and researcher at the Smithsonian, has been collecting beautifully preserved insects from this formation for a number of years. Most are small, but the level of preservation is remarkable, even down to the microscopic veins in wings, and most unusually for fossils, remnants of pigment too. Such a collection of exceptional fossil finds is often called a Lagerstätten, from the German storage place. The preservation here was likely due to a number of factors. One would have been reduced oxygen conditions caused by the blooming algae in the lake during the summer and the spring. As the algae died and sank, they would rapidly use up oxygen as they decayed. Such low oxygen conditions arrested decay and restricted scavengers. It's also been proposed that microbial mats in the lake may have also helped by sticking the insects and so stabilizing them on the floor of the lake. But the preservation of these fossils is even more significant than we originally thought. While examining a fossil of a mosquito, Dale noticed that one of the specimens had an abdomen that looked black and swollen. Using a scanning electron microscope and a mass spectrometer, a team led by Dale investigated the molecules preserved in the sample and found that large amounts of iron, specifically in the insect's abdomen, and traces of a molecule called porphyrin, a molecule that binds iron and oxygen in blood. This suggests that this was the mosquito's last meal. This is 46 million year old fossilized blood. Exceptional preservation is not restricted to fossils from geologically recent times though. The museum holds some beautiful fossils dating to 286 to 245 million years of the Middle Permian from what is today the Glass Mountains of western Texas. The Glass Mountains are part of an ancient reef system that formed in a shallow inland sea called the Delaware Basin, now exposed in the Apache Mountains and Guadalupe Mountains. The reefs around the margin of the Delaware Basin record shallow, warm water marine life of incredible diversity, a complete reef ecosystem. Some of these animals made their skeletons from calcium carbonate, the same composition as the limestone rocks in which they are now formed. During fossilization, though, silica replaced the calcium carbonate of the fossils. This is an example of permineralization. It also presented paleontologists with a wonderful opportunity, as silica is resistant to acids that will dissolve the limestones. As a result, the limestone could be etched with acid, releasing beautifully preserved silicified fossils. In 1939, Smithsonian scientist G. Arthur Cooper, at the time a member of the National Museum of Natural History's Department of Geology, began collecting blocks of limestone and building a fantastic collection of these Permian reef creatures, delicately spun in glass. And of course, there is perhaps the most famous example of exceptional preservation, the Burgess Shale, which provides a wonderful glimpse of early life on Earth over 500 million years ago. As we noted earlier, they were first discovered in 1909 by Charles D. Walcott, with over 65,000 specimens housed in the Department of Paleobiology. The creatures were buried in an underwater avalanche of fine mud in low oxygen conditions, preserving exceptionally fine details of the structure of their soft parts. But again, more of the Burgess Shale in a later episode. This is just a brief selection of some of the fantastic fossils that are available to paleontologists. We haven't even considered examples of more recent fossils that may contain remnants of DNA preserved by freezing or drying processes. Again, we'll get to those in a later episode. Hopefully, though, it's whetted your appetite to investigate what else the geological record holds, and perhaps for a visit to the National Museum of Natural History, where you can see some examples of these beautiful fossils on display, or examine some of these fossils at the museum's Curious Centre that houses fossils for public examination and study. Although, as we have seen, only a tiny proportion of life on Earth has become fossilised, that portion still represents an enormous cache of material for future paleontologists to examine. New discoveries of fossil bonanzas, the Lagerstätten, and new approaches and techniques in paleontology and paleobiology will likely continue to surprise and delight generations of scientists to come.